So now I would like to briefly overview all the papers introduced in this channel until now. I would like to, in a time series, and the first is this paper, Infer Metabolic Momentum or Infer Metabolic Direction for Moment Differences of Mass-Weighted Intensity Distribution. And this was first developed 2 years ago, and it is using times the intensity of this of the metabolomics data set with the corresponding weight of each biomarkers of each moleculars, and then using a location or scale estimators. Hodges here using the Hodges-Lehmann estimator since it is the optimal non-parametric robust mean estimator, or medium standard deviation proposed by Bickel and Lehmann, and it is the it has the same breakdown point as the Hodges-Lehmann estimator. So in this way, it is possible to infer the metabolic direction even without knowing the underlying structure of those spectra, of those mass spectra data spectra in the mass spectra data set, and then we show that this way is pretty valid, and the result is coincide with previous research. And then the second paper is mass dissimilarity based on differences in moments and sparsity. And here we show that current dissimilarity approach can be generally classified into two approaches. One is essentially it reflected the differences of mean, and another essentially reflected the sparsity differences. And then we further defining new mean dissimilarity and sparsity dissimilarity, also further defining dissimilarity with higher order moments, and for example based on standard deviation dissimilarity. And we show that show that this approach is pretty valid and can reflect the dissimilarity between the COVID-19 and control group. It can show that, and using a phylogenetic, and we further weighted all the biomarkers with a phylogenetic tree to further reweight it to achieve a better performance, more accurately reflect the matrix dissimilarity. They also reflect the relation between each biomarkers. And this matrix dissimilarity and because choosing the mean estimator is essentially very important, and it must be robust, since for example for the mean dissimilarity, it is essentially computing the mean of each row, and then computing the absolute differences between the mean of each two rows, and then we using a robust location estimator to estimate these sequences, these absolute differences. And here we use the Hodges-Lehmann estimator, but it must be robust, because if it is not robust, and then there is an issue that because in the omics data set there are often many outliers, and some at least maybe they are not outliers, but some biomarkers that differences overwhelmingly dominant other biomarkers. For example, maybe these differences can be 10,000, and others maybe just less than 100, and then it is so if you're using a mean, it is not valid. So because of such needs in the robust estimations of mean, and also further because there are some moments, and so this arises, and also other ideas from considering the replicability and reproducibility issues, and some PNAS papers, and this further rises the first paper, the robust estimation based on distribution structures. And the first is we consider the mean, the current two approaches, the trim mean and Winsorized mean, and the underlying principle is considered and deduce the trim mean inequality and Winsorization inequality. And then we further consider why the Winsorized mean is better than the trim mean, and it arises the ordinals and U ordinals and Knuth ordinals. And then we show that the ordinals and Knuth ordinals, although it might be invalidated by based on Li Shao, Wang Yang, and also Bernard's work, that there is a bound for the symmetric for the quantum average. So these ordinals and Knuth ordinals, although it might be violated in some cases, but the violation itself is bounded. And then we deduce new estimators based on the ordinals and Knuth ordinals versus the broad Winsorized mean, and we show that it is based on the ordinals, and although more biased than the Winsorized mean. And then we deduce the binomial mean and also stratified mean previously and introduced in the beginning. And then stratified quanta. I mean, and this already exhausted possibly all possible combinations in the class of linear combinations of order statistics in Daniel's work. And then we consider, and then after careful consideration of the underlying principle of Hodges-Lehmann estimator, the Hodges-Lehmann inequality is proposed, and also by Surfing's work, and then propose a generalized L statistics. It includes possibly all current mean estimators. It should be included in this class. And then weighted Hodges-Lehmann mean and medium Hodges-Lehmann mean are special cases of them. And medium Hodges-Lehmann mean is shown to be equivalent to the medium of means. And since medium of means was already shown previously by Devrov's their work, and therefore the Hodges-Lehmann estimator should be the optimal non-parametric robust mean estimator in this case. And then we show that because the medium of means there is a concentration bound, there is also a bound, so the medium Hodges-Lehmann mean should also have a bound for that, and the violation is also bounded. And then because then we're comparing the bias here, computing the bias, and also the simulation experiment shows that the medium Hodges-Lehmann mean is the optimum choice. And then the quasi-modal simulation is necessary to computing the medium Hodge slim mean and or relatively similar estimator because there is a combinatoric explosion here. So, and this the asymptotic validity of this bootstrap was the bootstrap was first proposed by Ephraim, and the asymptotic validity was proven by Bickel, Friedman, also Hammers, Jason, and Vervelby. And this is the first paper, and the second paper is considering the central moments. The central moments of this distribution. The central moments, the most popular the central moments is first we consider the Bickel-Lehman spread, and they show that they propose an estimator that is asymptotically equivalent to the sample standard deviation. And after considering, and it is essentially based on the pairwise differences. And then we consider the distribution structure of the pairwise differences. We found it was already proven by Hodges and Lehman in 1954 that the pairwise differences distribution is a monotonic. If you consider the pairwise is the first pair is smaller than the second, then the pairwise differences distribution is a monotonic increasing distribution with mode at 0. So therefore, the second central moment kernel distribution is a monotonic decreasing distribution. And previously we proved that in IEDS mean, and we proved that a distribution with a monotonic decreasing probability density function is always second gamma ordered. So therefore, this is always second gamma ordered. And then we consider the distribution of higher central moment kernel distribution, and since Heffernan already given the kernel function of this robust the kernel function of unbiased estimating the kth central moment by using U statistics, and then we consider how to further illuminate the structure of this pretty complex central moment kernel distribution when k is greater than 2, and then we decompose it into component quasi distributions. And then we show that it is indeed because it can be related to the pairwise differences. And then we show that the pairwise different distributions, different distributions, it forces this component, this central moment kernel distribution into a unimodal distribution with mode and medium close to 0. And in this way, and also later, the location invariant property of the central moment kernel distribution is also proven. And then and because of this, so it is possible to defining robust standardized moments, and not just robust central moments, but also standardized moments just by dividing it with the variance and after standardizing it. And then we consider another structure in the distribution by classifying the distribution also using the derivatives of the quantile average, but this time is with respect to the parameter. We consider the fundamental assumptions implication in non-parametric statistics, and it implies that when the parameters changes, all estimate should change asymptotically in the same direction. And we show that it is not always the case. So there is a very fundamental flaw in non-parametric statistics, and later we show that the central moment kernel distribution, although it might not be very strictly congruent, but the congruentness is generally it should be generally valid, that as nearly all symmetric weighted average should generally change in the same direction for the central moment kernel distributions as when the parameters change. And then we consider after exhausting all this generally non-parametric approach or semi-parametric approach, and then we consider parametric approach because even for the medium Hodges Lehman mean, the bias is still relatively significant. So first we review the current two approach is first Huber's approach, and then another is based on percentile estimators, and we show that they are all not robust to distributional misassumptions, distributional shift, and if we are assuming a Weibull, and then the actual distribution is log normal, even gamma, which belong to the same larger family as the Weibull, the bias can still be very significant. And then we show a solution is considering an estimator that is simultaneously consistent for both a semi-parametric distribution and a parametric distribution. Here we use and then we propose recombined mean is this simultaneously consistent for a location scale distribution and a symmetric distribution. We show that the exponential distribution has the unique property that if we use it as a consistent distribution, if we construct a recombined mean that is consistent for the exponential distribution, and then for the Weibull, gamma, Pareto, log normal, and generalized Gaussian distributions, and the recombined mean is consistent for at least one special case. And then we consider the quantile statistics, which also have the similar property. And then we consider the scenarios of the violation of this recombined mean or quantile mean, and we show that although it is possible to be violated, but this violation should be limited and bounded. Also, the quantile statistic is defined because it have a better performance in highly skewed distributions, and because the central moments it is inherently high, the gradus is inherently high, so therefore the quantile central moments generally have a better performance compared to recombined central moments. And then we consider you can compare the bias of the quantum mean here, the Pareto distribution. You can show that it is slightly better than the recombined mean. And then we show how to use a shape scale distribution as the consistent distribution. This was inspired by the Huber M estimator for the iterative reweighting. Then we consider even using multiple different shape scale distributions, and not just limited to one. For example, the Weibull, it can be extended to maybe even 4 or 5 different shape scale distributions, and this can be simultaneously consistent to multiple very different two-parametric distributions. And then we consider the variance. First we review the Daniel's very pioneering consideration that how to compare the efficiencies of various kinds of estimators. And then Bicker-Lehman, they suggested that meaningful comparisons of efficiencies can be of different kinds of estimators, even if they are not asymptotically coincide. We can study using the standardized variances, asymptotic variances, or efficiency bounds. And they are inspired by their standardized variance. We propose a scale standard error by multiplying a factor to the sampling distribution, and before we estimating the standard deviation of the sampling distribution, not after it. So in this approach, we can very easily compare the variance of many different estimators, and we found that the variance of these estimators are generally between median and mean, and also between median central moments and yield central moments. And this is also suggested by Bicker-Lehman's bound that they showed a lower bound for the efficiency of the tree mean with respect to the sample mean. This bound is monotonic, and the direction of monotonicity differs for distributions with different kurtosis. For example, if using the Lehman-Sheffield theorem, you can prove that for a Gaussian distribution, a very low kurtosis distribution, and the sample mean and unbiased second central moment are the unbiased minimum variance estimators. But for a highly kurtosis with a very high, the mean is infinitely large, and then the sample mean breakdown. So this is a very fundamental issue in statistics, that this will break down, and then we consider if, for example, for the medium, it will not break down for distribution with infinite mean, and then therefore it's suggested that for different estimators, for different kurtoses, the performance of estimators are very different. So there is an optimum estimator for different kurtoses. And then inspired by Lai, Robin, and Yu's PNAS paper, and we show that if you're using a combination, multiple combinations, more than in total more than 700 different combinations, and for so many combinations, we can infer the optimum combination by using Monte Carlo simulation, and then for each kurtosis there is an optimum combination, and we can also use the iterative reweighting, just like in Huber M estimator. We a fixed point, yes, oh no, the fixed point iteration. We can use that to optimizing the combination, and then choose the best combination. And then indeed it is not limited to this, and we also consider the robustness. It is now, it is shown in the original draft. We also consider how to measure the robustness, and we propose a weighted average, standardized average bias. And the weighted average is that we weighted, for example, there are 4 or 5 plus the generalized Gaussian distribution, 5 distributions. We counted their Google Scholar search results. For example, like here, we weighted this 5 distributions with their Google Scholar search results. Yes, and in this is a pretty practical way, but it is possible now. We can infer the bias of an estimator just using some Monte Carlo study, and it is relatively fair approach. Yes, and here, and we also discussed previous approaches to measure the robustness. For example, by Hampel's approach, in estimating the robustness. And also based on the Donoghue and Huber's proof in Hodges-Lehman estimator, we extended it to the high order moments. The breakdown point is also proven, and this is all papers. And then there is another paper. We later consider the non-asymptotic bias, and first the difficulties of analytically solving the order statistic distribution, the final sample distributions, is discussed. First, it is analytically solvable is almost impossible, intractable, and therefore, if using a Monte Carlo simulation, it is computationally very expensive, and therefore we consider. And we show that uniform distribution is the key. It is the key in the Monte Carlo simulation, and indeed it reflects the essential of randomness. And therefore, we show that it is possible to decompose this uniform distribution with several different sequences. And we first consider to decompose this uniform distribution with 12 sequences. The first is a arithmetic sequence, equi-interval arithmetic sequence, and then a beta distribution, a beta sequence from beta distribution with U shape, and then N shape, and then right school, left school, and then also monotonic decreasing, monotonic increasing, and then we consider some mixture about it. A very surprising result is that just using such 12 sequences, we can very accurately achieving a relatively accurate precision to decomposing the randomness of this uniform distribution into a relatively high accuracy. And so there, and then we later further in practice we use a stochastic approach. We randomly select generating random sequences and then selecting those combinations that can better approximate. But the successful of such theorems, it reflects that the randomness, it is in fact not as random as we imagined. That indeed for the randomness, it is maybe 90% of the randomness are indeed. It can be decomposed into some relatively ordered structures, and the truly randomness is just taking a relatively small percentage. Yes, and this is all the papers currently introduced in this channel, and if you're interested, feel free to contact me, and I'm also working with professors and students in quantum technique and also Berkeley to further improve these works. And thank you for listening.